Let's talk about something kind of mind-blowing. How do we have any idea what's happening in a rock formation literally miles under our feet? I mean, it's a total black box, right? But we rely on it for energy. Well, today, we're going to decode the secret language that tells us exactly what's going on down there.
I want you to think about it like this. An oil or gas well is kind of like a patient. And the engineer? Well, they're the doctor. But here's the catch. This patient is thousands of feet away, totally encased in solid rock. You can't see him, you can't touch him. So, how do you figure out if the patient is healthy, or maybe damaged, or performing at its best? That's the big puzzle we're going to solve.
So, here's our game plan for cracking this case. First, we'll lay out the mystery itself. Then we'll see how engineers actually listen to the well. After that, we'll dive into how pressure creates a unique signature, decode some of those specific fingerprints, and finally, connect all this detective work to real-world action.
All right, let's jump right into the challenge. The oil and gas we're after, they're not sitting in some giant underground cave. Nope. They're trapped inside the tiny, microscopic pores of a rock formation. We can drill a well into it, sure, but the rock itself, it's still a complete mystery box. We've got to find a way to understand its secrets without ever laying eyes on it. And the solution is, honestly, just brilliant. Instead of trying to see into the rock, engineers basically become detectives. They do something at the surface. Maybe they shut the well in or change its flow rate, and then they just listen. They listen really, really carefully to how the pressure downhole responds over time. And that response, the one that's recorded by these incredibly sensitive gauges, that's what we call a pressure signature. This whole technique is known as pressure transient testing, and it tells you pretty much everything. Every single well, every reservoir, every man-made fracture, it all has a distinct signature, almost like a fingerprint, that tells you the story of its condition.
So, if these signatures are telling a story, how do we read them? Well, engineers need a special kind of diagnostic chart to interpret all these complex pressure clues. And this right here is where the real detective work kicks off.
This is their #1 tool, the log-log plot. It charts two key things against time: the pressure change itself and its derivative, which, don't worry, is just a fancy way of saying how fast that pressure is changing. On this chart, the different patterns and shapes that these lines make, those become the fingerprints we're hunting for.
Now, before we get into the really complex cases, we've got to understand the two most fundamental clues you'll find in almost every single test. First up is wellbore storage, which is an effect happening inside the wellbore itself. The second is the skin effect, and that tells us all about the condition of the rock immediately around the well. Is it clogged up and damaged, or has it been stimulated and improved? Let's see what these clues actually look like on the chart. And here's how you spot them. Wellbore storage, that's easy. It always shows up at the very start of the test as a straight line with a slope of exactly 1. The skin, or the damage, is revealed by how far apart the two curves are. And engineers have this awesome rule of thumb. If the curves are separated by what they call 1 log cycle, there's no damage. If that gap is wider, you've got damage. If it's narrower, the well has been successfully stimulated. It's a simple visual check, but wow, is it powerful. Okay, so now that we've got the basics down, let's get to the really fun part. We're going to look at some specific case files. We'll check out the unique fingerprints left by different kinds of wells and see how engineers match these signatures to their suspects.
A really common suspect is a fractured well, you know? These are the man-made highways that can be the difference between a well that makes no money and a total gusher. Getting them right is absolutely crucial, but did the fracture job actually work the way it was designed to? The pressure signature holds the key.
Now, this is what's so fascinating. A tiny change in the data can tell a completely different story. Just look at the early signature row. If that plot shows a slope of 1/2, that means we have linear flow. Fluid is just cruising from the rock straight into a really effective fracture. But if that slope is 1/4, we have bilinear flow. That subtle shift tells the detective that the flow is actually getting restricted along the length of the fracture itself, which means it's not nearly as efficient as it could be. Incredible, right?
Okay, let's check out a new case file. Imagine you have a really thick layer of rock, but the well is only open to a tiny little piece of it. We call this a limited entry well. So, how would this unique setup change the flow, and what kind of pressure fingerprint would it leave behind?
The fingerprint it leaves is absolutely unmistakable, a slope of -1/2. This is such a distinct and unusual signature that it immediately tells an engineer exactly what's going on.
And here's the why, which is just beautiful.
That negative half slope is the telltale sign of what we call spherical flow. Because that opening is so small compared to the whole formation, fluid has to converge on it from above, from below, and from the sides, basically in a spherical pattern. The actual geometry of the flow path leaves a crystal clear, measurable fingerprint right there in the data.
All right, let's move on to a horizontal well. Its signature is even more complex. It's not just one fingerprint. It's a whole story that's told in 3 different chapters. Early on, you get this radial flow that circles around the pipe. Then, once that pressure signal hits the top and bottom of the rock layer, it changes to linear flow. Yep, there's that half slope again. And then finally, way late in the test, it can start to look just like a regular old vertical well again.
But what happens when the detective finds a clue that just doesn't seem to fit any of the usual suspects? What if this signature does something that looks physically impossible, like it's breaking the rules of our diagnostic chart?
This is a fantastic example of that. Sometimes, especially in gas wells, that storage effect we talked about isn't constant, because as the pressure changes, the gas itself expands or compresses differently, and the clue is unmistakable. The derivative curve actually crosses above the pressure curve. This should never happen in the simple models, so when it does, it's a perfect clue that points the detective straight to this very specific diagnosis.
So, we've seen how to read all these intricate clues and solve these underground mysteries. But why does any of this detective work actually matter? I mean, what's the point of translating all these pressure signatures?
Well, it's all about making smarter decisions. The detective's final verdict lets engineers diagnose problems, like confirming that positive skin is hurting their production. It lets them verify that a really expensive stimulation job was a success by seeing that negative skin. And maybe most important of all, it allows them to calculate crucial properties of the reservoir, basically how easily the oil or gas can flow, which helps them optimize how they produce that well for years to come.
So here's the bottom line. We started with this unknowable, invisible black box miles underground. But by understanding the secret language of pressure, engineers can translate these complex signatures into a clear picture. They literally make the invisible visible. It lets them understand and interact with a world they can never actually see.
And that leaves us with one last thing to think about. If pressure is a language that lets us decode the deep earth, what other invisible forces, in science and technology, maybe even in our own bodies, are we just now beginning to learn how to translate? What other secrets are just waiting out there to be revealed?